let's try this again and cultivate myself. I do apologize, I had a little bit of something I had to clear out of my sinuses there. I'm so sorry. Now, yes, okay, so the first thing is, I'm always trying to cultivate myself like xiu dao, to bring the Xing and the Ming together. Unfortunately, a lot of people may not even realize that there even is such a thing as cultivation, that it is possible to bring our Xing and our Ming together, which is the Xing is the postnatal kind of construct of the body, and the Ming is more to do with the prenatal or the destiny. These two aspects, when they are kind of brought into harmony through a lot of reflection and inner work, inner engineering, I guess you can say, then we can actually change our destiny, we can change our nature, and by doing that we can improve our health as well. So let's get on to this lesson. Bum, ba-dum, ba-dum. Oh, what does that say? It says CDR LAS, which is shorthand for Commander Lars. Kiwi Response Earth Defense Force. That was my idea. Just an idea, just for fun. Just for fun. Okay, so yes, I'm always trying to make things simpler and sum things up and try to condense things into something simple so that I don't talk shit for too long, and so yes, let's make some bullet points here. What are the important points? Okay, now I'm just still in the process of and you're fortunate because you're seeing how Commander Lars is in the process of becoming Commander Lars, so it's Rome wasn't built in one day, okay? But later on, it's gonna be Rome, and it's gonna be beautiful, and it's gonna be simple, and the bullet points are gonna be spaced evenly apart. Okay, let's try again. But let's start with 2 bullet points. Okay, but first, the big buzzword here. UFO. Yeah, okay, but why is that important? Okay, now we're going to talk about 2 things. Yeah, I think 2 things. Okay, energy generation, okay, and transport. Try and say in a South African accent. Transport, American accent. Okay, yeah, so energy generation and transport. These are 2 important things about this. Now I want you to just kind of forget everything that you have associated in your mind with this word, okay? I just want you to forget everything because it's a big buzzword, but it's kind of, or buzz thing that's it could have a lot of weird and not useful, unproductive and counterproductive connotations that will mess everything up. So we're just talking about the energy generation and the transport aspect of yes, and what do I need? I need some other kind of little fancy symbol here. I need one of those, which is meaning both of these means man-made. Okay, man-made, yeah, human-made, man-made. So we're talking about the man-made, UFOs, and I'm not talking about something that could just be a weather balloon, or it could just be swamp gas, or it could just be a jet engine that someone saw at night and they mistook it for something, or it could have been a shooting star, or it could have been, unidentified flying object. No, we're talking about the ones that are related to energy generation and transport. So something that was, and in regards to transport, we're saying basically, next generation transport, or something that is superior. Something that is just vastly superior to anything that we can see in use today in the military, or in the that civilians can see in the military, or in aviation, or in any conventional. Okay, right. So let's just do this. Okay, let's just do this, and then let's just put a big fat cross through that. Okay, so we're not talking about anything conventional. Okay, we're talking about something that is next generation, that is superior to jets, planes, hot air balloons, weather balloons, whatever. We're talking about something that has mastered, that is above what you would associate with what is physically possible. Okay, so it is basically it's great. Okay, it's greater than physics that we understand. It's some other kind of something else that can vastly outperform stuff by overcoming inertia. Okay, it can overcome inertia. Yeah, it can overcome inertia. It can overcome, here we have another gen, but I'll have to spell it. General, and special relativity. Okay, that's a bit wonky, but it's something that has solved the physics problem. It can overcome general and special relativity. So it's something that with regards to transport, it's something that allows us to get from Earth to the moon, or from Earth to Mars, a lot faster than you would expect. Something that is not using conventional rocket propulsion. It's not using aerodynamics in a conventional way. It's mastering the energy aspect. Okay, so hope we understand now that we're talking about something man-made. That's all this. Okay, good. Right, now let's talk about these two aspects here. Yeah, so there's energy generation. That has yes. So okay, energy generation. That has two subcategories here. Yeah, okay, we got to put a ray shown, and I'm not talking about as in my great grandfather's generation, or in the next generation, or in this. No, we're talking about generating energy. Okay, so now there's two different ways to generate energy. Okay, there's the magnetic way, and then there is a electrostatic. Electrostatic. Now, if you've ever had the opportunity to play around with some dielectric materials, such as this plastic here, you will find that even if you just kind of start to unwrap this plastic and take it apart, put it together, take it apart, put it together, you kind of feel there's like a... And it's not the air. You feel that when it comes together, it wants to stick together. And when you pull it apart, you can feel something's trying to pull it back together again. So there is an electrostatic charge. There is latent electrostatic charge in a lot of these dielectric materials, because they are, as you're moving them around, basically what's happening is as they move past opposite charges, they then build up charge. How does that work? Okay, let's talk about that. What it is. So let's talk about that. Yeah. What it is, charge, and how things build up charge. What do we need here? We need a negative and a positive. Negative and positive. Shall we go blue and red? Okay, we'll go blue and red. Okay. So talking about opposite charges, let's just do this conventionally. So let's just, okay, we need a, okay, so let's just say this is the ground, for example. Ground. And let's just say that, well, no. Because now you're going to associate ground with electrical ground, then you're going to think, oh, but it has to be this charge or that charge, but actually it just could be any charge. So let's just call it a surface, a surface, some sort of surface. It could be the surface of this, of this board here, or it could be the surface of this wall, or it could be the surface of my of this material here, or it could be the surface of my beret here. Okay, so let's say that surface is negative, just for the sake of it being negative. Okay, that has a negative charge. Now, and it doesn't have to have a very large charge, but just a little bit of latent charge, negative charge in there. Okay, now let's say we have another thing. Let's just say it's that. Can I draw a comb? I'll try and draw a comb. Okay. Okay, let's just say that's a comb. Now let's just say that the comb there has a positive charge. Positive charge. Okay. Now, the next thing we need is some swirly-whirlies. Swirly-whirlies. Okay, cool. Now then, yes, black, yeah, okay. So, it's a bit too close for me to depict the swirly-whirlies, so let's just move it a bit further away so that I can depict these swirly-whirlies. Okay, I'll put the comb up here. Gosh, terrible. Okay. Put the comb up there, that's the comb up there. And yes, as we mentioned, the comb has a positive charge, positive. Now, what that means is these, okay, I'm going to do it with black. Yes, so what that means is that these swirly-whirlies, where the positive is, are basically going in one direction like that. Going in that direction. These are swirly-whirlies. These swirly-whirlies are swirling in that direction, like that. These swirly-whirlies are swirling in, what is that, clockwise or anti-clockwise? It doesn't matter, you tell me. The only important thing is these swirly-whirlies are swirling in the opposite direction. They're swirling that way. These swirly-whirlies are swirling the other way. Okay. They're swirling that way. Cool. And we're just talking about a little bit of latent charge. It doesn't have to be a lot of charge, but it's just like, even in my hair, there'll be a little bit of latent charge. Like I can't feel it. When I take my beret off and on, and off and on, and off and on, I can't feel any, it's not break, I can't feel it breaking the lines of force. I'm going to get into lines of force in 1 second here, but when I put my beret on and when I take it off, I can't feel any bzz, 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 just like you maybe would if it was a very, very dry winter's day and you had a woolen shirt, and when you take your woolen shirt off and when you put it on and when you take it off and when you put it on and when you take it off and take it up over your hair, you can hear this like zzz, 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 zzz. And if you do it in a completely dark room and the room's completely dark, then you will see little little flashes of lightning, of little lightning bolt. Little electrical discharges will be coming from the short circuiting from your body or from your hair to the woolen thing. Okay, and why is that? Okay, we're going to see. But again, I'm saying when I'm taking my beret off and on, I can't. It's still happening, but just to a very, very small degree because of the humidity. Okay, there's too much humidity. Like you can hear the cicadas going outside there because it's summer here and it's a little bit humid, so there's not that much latent static charge in the air. Why? Because the humidity has changed, has messed with the dielectric permittivity of the air. When there's more humidity in the air, the dielectric permittivity, goes down. When there is, when it's very, very dry, when the air is very dry and a little bit cool, the temperature can influence as well. The dielectric permittivity goes up, which means it can store more charge. More dielectric permittivity, the greater the dielectric permittivity, the greater the charge. The less the dielectric permittivity, the less the charge. So right now there's not much charge. That's why if I had a woolen shirt now and I took it off and put it on, I might not even hear the discharges because there's not that much latent charge because of the humidity, because of the temperature, because of the season, blah, 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 blah. But here, we're just saying that there's opposite charge, okay? These swirly-whirlies are going that way and those swirly-whirlies are going that way. So if you put the clone closer and make it go that way, what's going to happen? What's going to happen between all these swirly-whirlies? What's going to happen between all these swirly-whirlies is that you're going to accelerate the swirly-whirlies, okay? The swirly-whirlies are going this fast because there are a certain amount of charge. Those ones are going in that direction, these ones are going in that direction. But when you have two oppositely spinning swirly-whirlies, and when you pull them past each other, it spins them up more. It's just like if you would have a gyroscope, no, not a gyroscope, it functions like a gyroscope, but it's a spinning top. If you would have a spinning top and it's kind of like not spinning very fast and it's almost about to fall over, but if you spin it up really fast, what happens? It picks up more inertia. Okay? Inertia and charge are related, and later you're gonna see how, when we have mastered the charge, how it can make this, we're calling it a UFO, but actually it's something that has been engineered. Again, it's a next generation. It can overcome the inertia, and it can overcome general and special relativity. It can even surpass the speed of light. We're going to see how that happens in one moment. Okay, bear with me. I might do it in the next video again. We're just taking our time. Again, Rome wasn't built in a day. We're just seeing how Commander Lars is becoming Commander Lars. Okay, right. So when we pull these two surfaces, past each other, if we pull them past each other too fast, what happens is those two swirly-whirlies, they don't have time to connect. But if we pull them, so it doesn't necessarily mean that the faster you pull them past each other, the faster the charge. What you have to do is, if they are spinning at a certain velocity, a certain rate, then the closer you can get to that rate of spin and synchronize it with the velocity of the pull that goes past it, what happens is those two swirly-whirlies will connect and they'll want to come together. But because you're pulling them apart, they're going to spin up. You're going to increase the inertia and the charge of the two. And what happens then is that you pull it apart. Basically, these swirly-whirlies go doing, 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 and they pull back into the material, and that increased inertia is taken up into the material, and then you have an increased charge in the material. Okay, so hopefully you understand that now. So just remember this thing in your mind about the two swirly-whirlies and how when they go past each other, they get spun up a little bit more. Okay, cool. So now, Wimshurst machine. Yeah, okay. So electrostatic, that's what we just explained. Okay, that is because we're talking about energy generation. So the thing that I just explained is the basic principles of electrostatic energy generation. Okay, then the next will explain magnetic, but the first one is electrostatic. And have you seen a Wimshurst machine? Do you know what a Wimshurst machine is? Okay, well a Wimshurst machine works with the exact same principle that I just explained. Okay, it has two big discs. So let's hopefully your imagination is good enough, and you can understand that there is there's a disc behind that disc, and they have these they have these sections on them. Okay, they have these big flippy floppy sections on them like that. Okay, just use your imagination. Okay, in your mind, just balance out and reorganize the way I drew it, and so telepathically connect your mind with my mind, and then both our minds' eyes just synchronize it and make it good. Okay, right. So this is a dielectric material, and these are conductors. So this is a dielectric material, dielectric, which means it has a good permeativity, like a good dielectric permittivity. Like this stuff here, it can store a shit ton of electric charge. Okay, you can even make a very big electrostatic capacitor like this, which all you do is you use a conductive foil or conductive material. The stuff here is conductive material, like this one. This one here is a nylon material which has interwoven threads of silver and other silver-looking material, and this one is copper. This one is basically a nylon material with copper thread interwoven in it. And so what you do is you plump this in the middle, and then you plonk a big sheet of conductive material on each side, and then another sheet of the insulated material, so that you can roll it up, or you can keep it flat or whatever. And then what you do is you charge it up with a. Okay, let me show you what you could do is you could charge that bastard up with this right here, which is a 30. Well, actually, it's 5 kilovolts to 30 kV. So this is a solid state electrostatic generator. So this will basically it plugs into the wall, and then it's got a transformer and a volt multiplier and some other circuitry that just bumps up the voltage, well, converts it to DC, so it's AC coming in, alternating current, which is changing in time, and it's flipping it over to direct current, which is not changing in time, it's just negative and positive, and then it's stepping it up through a volt multiplier to take it from either 12 volts or 240 volts DC right up to 30,000 volts DC, which is a very high electrostatic charge. And then you can just put each negative and positive on each one of the plates there, and that'll boom. And oh man, if you charge that sucker up right there, it is dangerous. I learned the hard way, but it's fun to play with once you know what you are doing. Okay, so this is a this is an electrostatic generator. Okay, it's called a excuse my dyslexic tutoring. Wimshurst machine. Okay, so this is a Wimshurst machine. So what you have is you just have two counter-rotating dielectric discs. So they're not flimsy and floppy and floppy like that. They are solid, probably like 5 millimeter thick, perspex your perspex plastic, hard plastic, or maybe some kind of glass, or maybe what's the other stuff called? There's other stuff that has a very, very high dielectric permittivity. It can store a crazy amount of charge. It looks like perspex, but it's not perspex, but it's similar. And what you do is you have them counter-rotating, so those little swirly-whirlies that are between them, some will basically, there'll be some latent charge in there because it's such a good dielectric. It's already got a little bit of latent charge in there because of the properties of material. So when you start moving them counterclockwise, and basically it's the same as going like that, but just in a circle, it's moving them past each other, so it's spinning up the vortexes and increasing the inertia, increasing the charge within the atoms, okay, within the atoms of the material, okay, and then it has these what do you call them, sectors. So that's a dielectric, and then we have conductive sectors, and then we have these conductive sectors, and then on each side we have a little a brush like that, and then so the brush just as that rotates freely around, and then the brush just brushes there and then collects the charge, and then usually it goes into a big ass capacitor. A capacitor is what I just explained, is that thing that I just showed you, and then the capacitor builds up the charge, and then sometimes it has a spark gap like that, and then when it builds up a charge when the between these 2 points, when the air also has a certain amount of dielectric permittivity, what happens is when the charge gets so high that the dielectric permittivity of the air says ah, then what happens is it goes bang, and it makes a big spark, that because it's called dielectric breakdown, okay, of the medium. So and then it reaches dielectric breakdown, and it'll basically go bang, 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 bang. If you're rotating it like that, it'll go bang, bang, and then if you rotate it a little bit faster, then it'll start going bang, 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 a little bit faster. And then if you rotate it really, really, really fast, sometimes it'll get to a certain point where it won't go bang, 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 bang any more faster, because you're spinning it too fast so that those vortexes can't connect. So now, do you remember those vortexes? Let's just say we're looking at these. Okay, right now we're zooming in and we're looking at it side on. So, and then we have one side is negatively charged, and the other side is positively charged, like that. And then we have the swirly-whirlies. We have the positive swirly-whirly going in one direction, and then the negative swirly-whirly going in the other direction. Okay, I think I messed that up, but anyway, you get the picture, right? Damn, that was supposed to be that way, and that was supposed to be that way. So what's happening is that when you spin it, basically what you end up is you end up with snapping lines of force. You end up with snapping lines of force. Basically, I think Michael Faraday, one of the pioneers of electrical engineering, before electrical engineering was infiltrated by this craziness, and when the understanding, the science of electrical engineering was in its prime, and if we had have continued on that, society would be a lot different. We'd have electrogravitic, what we conventionally call anti-gravity. We'd have that between cities. Everyone would have instead of owning a car, you would have your own zero emission spaceship parked outside that either you could zoom down to McDonald's and get your hamburger, or you could take your girlfriend on a honeymoon up on the moon or on Mars, or you could fly through and see the crazy volcanicness of Mercury or something, and then you could fly back down, and that we would have that, okay, and we wouldn't be working like slaves 40 hours a week for nothing, and we would also be able to participate in the intergalactic economy, which is happening because there's many other civilizations like this one, and there's people on aliens or extraterrestrials, whatever you want, other life forms like us. Some of them look similar, some of them look different, some of them look kind of the same but they're different, blah blah blah. Okay, and of course we would have more responsibilities. We'd have to basically enforce some kind of restrictions on this on Earth to kind of and have more laws and sophisticated courts and things to prevent this kind of thing from being misused, or someone from putting a nuclear bomb on it and delivering it to an enemy country. I mean, it looks like it's almost for a reason that things are the way they are, But I'm just thinking that hopefully it's going to change soon. So this is what this is: snapping lines of force. Is that going to? Yeah, hopefully that should be fine. Yeah. So snapping lines of force. Okay, this is a electrostatic generator. Snapping lines of force. Okay. Right. So snapping lines of force, electrostatic. Yeah, Wimshurst machine. Now, just remember that understanding that we just explained. So I'm just going to have to draw something new here. So I hope you can remember how electrostatic charge generators, like a Wimshurst machine that I just explained just now, how it works. And now we're going to talk about how we get faster than the speed of light, or how we get to go really, really, really fast, and even faster than the speed of light. So there's charge all around us, okay? Like I just explained, every material has a certain dielectric permittivity. The air that we breathe has a certain dielectric permittivity. We are an electrostatic generator. As we are breathing, the air is going into our lungs and it's going into our bronchioles. Our bronchioles have a certain are made of a certain dielectric material, and when the oppositely charged air goes past the oppositely charged bronchioles, hey presto, the swirly-whirlies get spun up in opposite directions, and then we have charge coming into electric charge coming into our body and charging us up, and so look, this technology right here has medical applications as well. It's not just for transport or energy generation or just two applications. No, this is very, very, very many applications here. Okay, so now there's electrostatic. Everything has a certain amount of dielectric permittivity. I messed that up. Let's put it there. So let's just say that this is the Earth, blah blah blah, blah blah blah, blah blah, and then maybe I should draw the atmosphere on a blue, and then that's the atmosphere. So the atmosphere has, because the atmosphere is a gaseous matter, and because there is more matter, there is more material, more gas, matter, atoms. There's more atoms in the Earth which have a certain amount of dielectric permittivity than out in space. The space in space is closer to a vacuum. It's not a complete vacuum, but it's closer to being a vacuum. Okay, so inside of the Earth, these things, we're calling them UFOs, or call it a flying saucer, or call it a TRB-3 or a flux liner or whatever. When they're going through the atmosphere, they can pick up more charge, okay? And they can slingshot themselves through the atmosphere like that, okay? Very, very, and they can build up because there's more dielectric permittivity. As they are going through, they are the swirly-whirlies between the craft and the atmosphere around are connecting, okay? And when it goes faster, the swirly-whirlies get spun up even faster. And if you have the means to turn the fuselage, the fancy word fuselage, that just means the hull of the spaceship, the hull of the craft. If you can if you have the engineering, if you engineer the hull of the craft such that and you use the right materials and you use the right sectors and all that crap that we explained with the Wimshurst machine, and you make the outside fuselage of the craft like that in relation to the dielectric medium around the craft, so that the faster you go, the more charge you build up, and that charge is fed back into the engine of the ship and used to propel it further. Okay, and that's how this little guy right here, okay, that right there will reach a certain point where it goes whoop and it flips around, okay, and it gets inverted, and you go past the crossing point of light, okay, you traverse, you're probably going to end up with something like a light boom, like a sonic boom, when you cross the sound barrier, right? Well, when you get to a certain velocity and you reach a certain point, a certain threshold, you reach a certain threshold where you are going so fast and you're having, okay, because what this basically says is E equals mc squared. What it says is that the faster you go, the more inertia you build up and the more mass. And the more the mass, as you go faster, there's more inertia, more mass, which means that you need more. You need more energy to make it go faster. So mass mean m is mass and c is the speed of light and E equals energy. So it means that as you accelerate, as you increase the velocity, the mass increases by the square of the speed of light. So as you start to go faster, it becomes more difficult to go faster, is what E equals mc squared says. So according to E equals mc squared, it's impossible to go faster than the speed of light. But what is happening with this device is that the faster you go, the more charge you build up, and the more charge you build up, the faster you can go. Okay? So I'm not a mathematician. I can't mathematically explain this to you, but some quantum physics, like what's his name, Salvador Salvador, someone or other, the guy that made all those patents, those US Navy patents, and he's got like hundreds of patents, I think, that all of these different, all these different craft work, okay? And he's got hundreds of patents, and he explains it. Okay, he explains the math. So if you want to see the math and don't just take my word for it. If you want to see the math, and he'll explain it, how this gets inverted, and how when you cross the light barrier, basically you cross the light barrier, and then you end up basically in hyperspace, and then of course you need other electromagnetic systems as well to kind of balance the thing somehow, and when it's going faster than the speed of light. Okay, so I think I'll leave it at that. That's basically just talking about electrostatics and how the faster you go, the more charge you build up, and eventually you can cross the light barrier. And magnetic is also a way of generating energy, but magnetic is what you're doing is you're crossing the lines of flux. Okay, magnetic. It's just, okay, I'll finish this lesson off with this, okay? So magnetic, okay, is lines of flux, and electrostatic, what did I say? It's the swirly-whirlies. It's the lines of flux, and I think this one is lines of lines of force. Let me think about this. I'm just thinking about this, okay? Rome wasn't built in a day, and I just need time to kind of consider what I'm actually trying to say here. But there's something. There's something here. I'm going to figure it out, okay? Magnetic is lines of flux, and electrostatic is something else that I wrote here. Was it that? I don't know. Okay, that's this lesson for now, and later I'm going to make more points, and I'm going to make it easier for you to understand.